Well, hello, good people. I have something to show you. Okay, one second. We'll see how this works. Here I have a battery. This battery is then connected through a series of wires. You can see if you follow this. Well, okay. You can see if you follow this red wire down. It's connected to a little light bulb right here. That little light bulb is then connected to this little switch right here. And so here's what I'm going to do: is I'll hold this little light bulb up where you can see it, and I'm going to flip the switch. And when I flip the switch, you're going to see something happen. Here we go. Wow, never mind. You really can't see if I go that way. So forget that. I'm just going to flip the switch right here, and you're going to watch this little light bulb. Are you ready? Let's turn off the lights so that you can see it a little bit better. One second. Okay, here we go. Are you ready? 3, 2, 1. Ta-da! The light bulb glows. Now you say, Miss Wilson, that's actually not that interesting. But thank you for all of your really nice attempts to show me that picture of the little light bulb lighting up. But you say that's all very simple and I'm not actually seeing really anything that interesting there. That's fair, because this is what we call a simple circuit. All that it is it's a little battery connected to a little light bulb. That's the whole story. Nothing really complex or interesting there. Or is there? If you think about it, really think about it, even a simple circuit is highly, highly complex. How do we have a setup where you have a light bulb that's not glowing, you flip a switch, and all of a sudden there's light there? What happens so that you can have no light, flip a switch, and then there is light? To understand how a simple circuit works, you're going to need to understand a few things about these 4 concepts: voltage, current, resistance, and Ohm's law. And those are our 4 topics of the day. We'll start today by talking about voltage, then we'll talk about current, we'll talk about resistance, and finally we'll conclude our class today talking about Ohm's law. Let's start by talking a little bit about voltage. When we're talking about voltage, or what I like to call electric potential difference, we are talking about what makes charges go. You know that in order for a light bulb to light up, charges are going to have to flow through that little wire, through the light bulb, in order to make the light bulb glow. Well, the question is, what actually makes the charges go through the light bulb? Why are they motivated to move? What is the shove that gets them going? Well, let's take a look at something a little bit more familiar. Here I have a soccer ball that is sitting at the top of a ramp. Oh no. Try again. Okay, sure, yeah, that's good enough. Here I have a soccer ball that is sitting at the top of a ramp. If I let that soccer ball go, then the soccer ball will roll down to the bottom of the ramp like this. Before we answer what makes charges go, can you answer the question, what makes a little soccer ball go down the ramp? Now, there are a few different ways to answer this question. Most students, when posed with the question, what makes a soccer ball go down the ramp, they'll say something like gravity, which is a good answer, but it's not the most thorough or complete answer. Here would be a more complete answer, is to say, well, gravity creates a gravitational force on this soccer ball which has mass. That gravitational force then pulls on the soccer ball, causing the soccer ball to accelerate on the way down the ramp. That's one way to talk about it. Another way to talk about it is to say that gravity creates gravitational potential energy. And this soccer ball starts up here with gravitational potential energy. That energy then converts into kinetic energy. As the soccer ball loses gravitational potential energy, it gains kinetic energy as it falls. That's another way to talk. Well, similarly, there are multiple ways to talk about why the charges are going to move in a wire. And the answer that we're going to use today is we're going to use this concept of electric potential difference. And we're going to say that electric potential difference is what causes those little charges to move in a wire. Now, when we say electric potential difference is what causes charges to move in a wire, a lot of students go, And so before we talk about electric potential difference here, we're actually going to start by talking about gravitational potential difference. And before we talk about gravitational potential difference, we're actually going to talk about gravitational potential energy. Then we'll use our understanding of gravitational potential energy and gravitational potential to understand what we call electric potential and electric potential difference. Let's start by talking about gravity. Here, I have, wait for it, some bleachers. Here are some bleachers. Now, you could imagine that we could have some students who come to sit on these bleachers on the day of the big football game. So you could have one student who comes and sits here on the bleachers. Okay, yes, there you go. You can have arms too, and a smile, of course. We could have another student who comes and sits here on the bleachers, at this bleacher right here. Yes, thank you. Yes, my drawing skills are pretty remarkable, if I do say so myself. You could have another student who comes and joins his buddy here on this bleacher right here. Let's give them hair, shall we? He has curly hair. He has spiky hair, but you really can't tell, honestly. Okay, and then this is Sarah, who is obviously a girl, and she came with her boyfriend, Emilio, who is right here. There's Emilio. I'm trying to make their hairstyles unique and different, but I don't really know how it's going for me. Okay, Sarah and Emilio came to the soccer game, and then Sam came to the soccer game. Here's Sam. I think I said football game earlier, and now it's a soccer game. I don't know why the sport changed, but sorry, I just wanted to draw Sam a little bit better. Okay, here's Sam. Sam, oh wow, okay, I don't mean to make Sam enormous. Okay, take two. And by two, I do mean three. Sorry, everybody. I'm letting go of my perfectionistic tendencies, but obviously not very well. Okay, here is Sam. Sam's happy to be here. Sam is here with his friend Samantha, who also happens to go by Sam. So we have Sam and Sam up here at the top. And then one other person shows up to the game. And when we say that one other person shows up to the game, I do want to remind you, of course, that we are always considerate in the way that we speak about people. We never make fun of people based on their physical appearances. But I am going to draw the last person who comes to the game today, and that is Charles. There is Charles. Okay. Now all the students have come to watch the game. And all of them are sitting on different bleachers here. Well, each of them, we say, has different gravitational potential energy. If we wanted to talk about different people who have different gravitational potential energy, we would say that the people at the bottom here probably have the least amount of gravitational potential energy, while the people here at the top have the most gravitational potential energy. But even they don't all share the same amount of gravitational potential energy. We know that gravitational potential energy is equal to UG equals mg delta H. And so we know that not even all the characters up here at the top have the same amount of gravitational potential energy, because it does appear that Charles has slightly more M than Sam and Sam do. And so we see that Charles has slightly more gravitational potential energy. Now, what they do have in common, Sam and Charles, is they all have the same, wait for it, change the color, so cool. They all have the same G delta H. Because Sam and Charles are all sitting at the same height, and they all are experiencing the same strength of the gravitational field, which is G. Meanwhile, Emilio and Sarah, they also both have the same G delta H in common with each other. And these two guys here, this is Juan, and this is, oh no, I forgot to name him, Steve. Steve and Juan are both here, and they both also have the same G delta H. So not everybody has the same gravitational potential energy, but everybody who's sitting on the same bleacher has the same G delta H as each other. Sometimes it's helpful to talk about how much gravitational potential energy an object has, how much mg delta H it has. But other times we found it very helpful to talk about how much G delta H something has. The reason why it's helpful to talk about how much G delta H something has is because G delta H, do you see, doesn't depend on who's sitting there. Anybody who's sitting on this bleacher right here would share the same would share the same G delta H as Sarah and Emilio. And anybody who's sitting on this, try again. Okay, we could do it. Oh, never mind, it won't let me. Okay, pretend. Anybody who's sitting on this bleacher right here would have the same G delta H as Steve and Juan. And anybody who is sitting on this bleacher, up at the top, the very tippy top bleacher here, would have the same delta H, or G delta H, as Sam and Charles. And in fact, we could actually talk about a bleacher as having a certain amount of G delta H, even if nobody's on it. Like this bleacher here has a certain amount of G delta H, even if there's nobody here to experience it. You can see that this could very quickly become a very convenient way of talking about how much potential energy a certain spot has, or how much potential energy somebody would have if they were to sit at that spot. This concept of G delta H is what we call gravitational potential, and we represent it with a capital V, lowercase g subscript for gravity. And how much gravitational potential you have is equal to G delta H, where delta H is how high up you are on the bleachers. This could be very, very applicable for all kinds of things. When I think about gravitational potential, I like to think about elevation in general. If I'm at a high elevation, I have a very big gravitational potential, or high gravitational potential. If I'm at a low elevation, then I have low gravitational potential. But why I like to think about it in terms of elevation is because the top of a mountain has high gravitational potential. It has a big G delta H, whether or not I'm there to experience it. The bottom of the mountain has low gravitational potential, regardless of whether or not anybody's there to experience it. This is a concept that is going to translate over very nicely into the electric world. But before we transfer it and before we start talking about why this is really going to be applicable for the movement of charges, can you please tell yourself what is gravitational potential and how is it different than gravitational potential energy? Now, gravitational potential offers us a new way of talking about the soccer ball sitting on the top of the ramp. You could say that the soccer ball sitting on the top of the ramp goes down because the force of gravity pulls it down. Or you could say it goes down because it starts with gravitational potential energy and it ends with kinetic energy. Or you could talk about the soccer ball goes down because it goes from a place that is higher potential to a place that is lower potential. It experiences a gravitational potential difference, and as a result, it goes from a place of high potential to a place of low potential. These little guys here show us that this thing is true. That mass will always move naturally from a place of high potential to a place of low potential. Let's say that they wanted to turn these bleachers into a playground, and so they started to install some slides. Here's a slide here. There's a slide for Sam. Here's another slide. Oh, well, that's kind of a tall slide, but that's okay. Here's another slide next to Juan. Here's another slide next to Sarah. And lastly, let's put in a little mini slide here. Okay. Now, we say that things naturally are going to move from a high potential place to a low potential place. Sam is naturally going to slide down the slide. If there is a path from a high potential place to a low potential place, a path being like a slide, then Sam will go from the high potential place to the low potential place. But what almost never happens is you're never going to see somebody like Juan start suddenly floating up the slide. Things won't naturally move from a low potential place to a high potential place. In order for Sam to move up the slide, Sam would have to actually put in a little bit of work, and I do mean work, like work as in force times displacement. Juan here would have to put in a little bit of work to go up the slide. But gravity will naturally, the gravitational field will naturally pull things down from a high potential place to a low potential place if given a path. This is also true of our little soccer ball sitting on a ramp. Let me draw it here. We shall draw it in pink. Here is a ramp, poorly drawn. Here's a soccer ball. This soccer ball starts out at a high potential place. Gravity will naturally pull it to a low potential place. Now notice this, that the soccer ball won't actually move from a high potential place to a low potential place unless it has a path to get there. The ramp provides it a way from the high potential place to the low potential place. And if it has a path between the high potential place and the low potential place, it'll naturally travel there. But it won't travel if everything is at the same potential. If a soccer ball had a path between a medium potential place and a medium potential place, it wouldn't move. What you need in order to make something move is you need what we call a potential difference, a delta V. Because there is a high potential and a low potential, you have a difference in potential. And that difference in potential will cause the soccer ball to roll, to move from the top of the ramp down to the bottom of the ramp if given a path. If it has no difference in potential, there's no reason for it to move, and so it'll just stay where it is. This is all going to be used for when we create a circuit. If we want charges to move, here's the idea. If we want charges to move, we're going to create a high potential place and a low potential place, and then provide a path between the high potential place and the low potential place. Charges will naturally move between the high potential place and the low potential place. And that's the idea. Let's go ahead and take a look back at our drawing over, here. Sorry, I forgot where it was. Okay. Here's what electric potential difference is. Electric potential difference is very similar to gravitational potential difference, except with gravitational potential difference, we have like a literal high elevation and a low elevation. And that's not the case with electric potential difference. With electric potential difference, we have something more like this. Say that I had a metal plate, and I got this metal plate super charged up with a ton of positive charge. I just threw a ton of positive charge on this metal plate. Then say I had another, oh, move out of the way, buddy. Okay, not like that. Okay, okay, sorry everybody. Okay, you can do it. Let's move you over. Let's move you up here maybe. Okay, get out of the way. Yes. Okay. So I have this high potential plate, or I have this positively charged plate right here, and then I have this negatively charged, let's say that I just had like a sheet, oh gosh. Let's say that I just had a sheet of metal here, and I got this, Why can I not draw straight? This is just embarrassing for me, honestly. My kindergarten teacher would be quite ashamed, I do think, at this point. Okay, come on. Come on. Undo. Okay, here we go. Nice and straight-ish. Yeah, okay, good enough. Let's say that I put a lot of negative charge here on this little plate right here. So I have a positively charged plate and a little negatively charged plate here. Well, hey, if I put a little positive charge right here, this little positive charge is next to a bunch of other positive charges, a place where it does not like to be. And so we'd say that this little positive charge has a ton of potential energy. If I took my fingers and I held this little positive charge here, then I would have to hold it really, really tightly because that thing would want to go flying. It would want to go flying towards the negative plate. We say it has a lot of potential energy because it has a lot of potential to start moving. So we would say that this little thing right here has a high potential energy. But it's not gravitational potential energy, it's electric potential energy. If I had a little positive charge down here, contrarily, this little positive charge would say, I'm very happy where I am, nice and close to these negative charges. If I were to hold this thing here and when I were to let it go, well, it wouldn't have a lot of potential to move, so we would say that this thing has very low potential energy because it doesn't have a lot of potential to move. This leads us to talk about what the actual potential is like at these places. we would call this place right here a high potential place. And we'd call this place right here a low potential place. We call this a high potential place because if a positive charge were here, it would have a lot of potential energy. We call this a low potential place because if a positive charge were here, it would have very little potential energy. This is similar to, back over here. This is similar to the way that we talked about the bleachers. The top bleacher is a high potential place because if someone were to sit on the top bleacher, they would have a lot of potential energy. This spot has a lot of G delta H. The bottom bleacher is a very low potential spot because if somebody were to sit there, they would have very little potential energy. This is why it's very helpful to talk about potential instead of potential energy, is because potential allows you to talk about how much potential energy something would have if it were there, but you don't actually need anything to be there to experience the potential. Notice that we always define potential based off of what a positive charge would experience. I would call this a medium potential place because a little positive charge placed here would have a medium amount of potential energy. I call this a high potential place because a little positive charge placed here would have a lot of potential energy. But if I placed a little negative charge here, oh, please do ignore the bells. A little negative charge, oh my, I'm stuck. A little negative charge placed up here would have very low potential energy, but we still call it a high potential place. That's because we base potential based off of what a little positive charge would experience. So, here's the idea. The idea is if we can create a high potential place and a low potential place, and we can make a path between them, then charges will flow. The same way that a little soccer ball, if you have a high potential place and a low potential place, and you make a path between that high potential place and the low potential place, that little soccer ball will move. Same thing will happen with charges if we can give a little path between them. The way that we do this in a circuit is we use a battery. This is a battery, not a Lego. A battery is basically made of two sides, and don't tell any electrochemist that I drew a battery this way because it's totally a lie, but it does get the general principle across. A battery is made up of, and actually I'm going to move my battery, sorry to be obnoxious like this, but I want my battery down here so that I can draw a little bit more here. Okay, here is my battery. My battery is made up of two sides. It has a high potential side and a low potential side. One side of the battery has a lot of positive charge. The other side of the battery has a lot of negative charge. This means that a little positive placed right here would say this is a very high potential place. And so we say that this terminal is the high potential terminal. We say that this terminal right here is the low potential terminal because a little positive right here would experience very little potential energy. We create a high potential place and a low potential place. Now all we have to do to get charges to flow is to create a path between the high potential place and the low potential place. So what we do is we use a little wire to make our little path. This little wire allows a path for the charges to go from high potential to low potential, just like the ramp allows the soccer ball to go from high potential to low potential. And bam, you get charge that's flowing. And if that charge flows through a little light bulb will light up. That's the general concept. Before we talk about equations here, can you please check with yourself really fast, check in your brain, how do we use potential difference to create the flow of charge in a circuit? Explain that to yourself. Hey, notice here once again that I have a difference in potential between the high potential place and a low potential place. This is why we call it electric potential difference. If I just had a high potential place and I did not have this low potential part of the battery here, if this did not exist, if I just had a high potential place like this, well, no charge would flow. You need a difference in potential, a high potential place and a low potential place in order to get charge to flow, the same way that you need a high potential place and a low potential place for your soccer ball in order to get your soccer ball to move. Let's talk about how you calculate this electric potential difference, this delta V. Well, if you remember from our bleacher situation, we said that from the bleachers that delta VG is equal to G delta H. Now, this equation comes from somewhere, and really, and I'm going to have to move this thing. I just know that I will, so I'm going to go ahead and do it right now. Okay. This equation comes from somewhere, and really, the place where this thing comes from is it comes from the idea of potential energy. We say that delta VG is how much potential energy something would have if it were there, but we're going to take how much potential energy it would have, and we're going to get rid of the mass there. Just like how in our picture over here, we wanted to find out how much potential energy or how much electric potential, how much gravitational potential Sam and Charles had. Well, we want to know how much GH they have without their mass, how much potential energy they have without their mass. So the way that we find this is we take their potential energy, their delta UG, and we divide it by their mass to find the potential of that spot. Well, when we do this, and oh darn, now I have to move this thing again. I preemptively moved it, and now I just have to move it double. Well, okay, well, here we go. Now, in order to find this, that gives you delta VG is equal to mg delta H divided by m. And your m's will go away, and you're just left with this top equation, that delta VG is equal to G delta H. We can do something very, very similar for electric potential difference. We say that, oh no, please stop that. Okay. Can we undo that other stuff? Okay. We say that electric potential difference is equal to how much potential energy a charge would have divided by the size of that charge. Again, very similar to what we have here. It's how much electric potential energy something would have divided by the size of that charge. And similar to this equation where you have delta VG equals G delta H, well, G is the strength of the gravitational field and H is your displacement within that field. If you look at our bleachers example, once again, I keep trying to go down there to look at my bleachers example, but we all know it's actually up here. If you look at the bleachers example again, why do I have these little guys down here now? Okay, this is what I want. Okay, if you look at our bleacher example again, we know that there is a gravitational field that is constantly pulling all things down from high potential places to low potential places. If we wanted to talk about how much gravitational potential difference between one place and another, we would say, okay, well, I want to look at this place versus this place. I want to look at my difference in height here, and we say gravitational potential difference is equal to the strength of the gravitational field times the difference in potential, the difference in height between the two places where you're looking for the difference in potential. Well, the same thing applies over here. If I want to find the difference in potential between two places over here, over here, hello, yes, thank you. No, not that. Bye, 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 goodbye, thank you. Okay, we can do this. Give me the color green. Okay. There is, similarly to the way that there's a gravitational field there, there's also an electric field here. The electric field goes from the high potential place to the low potential place. But you can see that it also goes from positives to negatives, which is what we saw in our last lesson on electric fields. So you have an electric field that goes from the high potential place to the low potential place, something like this. If I wanted to know the difference in potential between two places, say like right here and right here, I would want to know the difference. Wait, try again. I would want to know what's my difference in position between these two places. I'd want to know like my difference in distance, or my difference in distance like this, or my difference in length like this. In this equation, I'm going to say that similarly to how delta VG is equal to G delta H, I have over here that delta VE is equal to the strength of the electric field, just like the strength of the gravitational field, times the change in distance within that field. I'm going to use delta L here, and I'll explain why I use delta L and not delta X momentarily. But that is the main idea, is that delta V is equal to the electric field times your movement within that, your distance or your displacement within that electric field. And that gives you the electric potential difference between two places. Let's talk about how this looks in a wire. Well, in a wire, you have a high potential place and a low potential place. That high potential and that low potential place is going to set up a little electric field inside this wire here. That little electric field is going to point from high potential to low potential, as all electric fields do. The distance that you go from the high potential place to the low potential place is a distance delta L. I use L because it's the length of the wire. So you go from you have a potential difference between the high potential place and the low potential place that's equal to the strength of the electric field set up in the wire times the length of the wire, which is the length that a little positive would have to travel to go from the high potential place to the low potential place. And that is a little something on electric potential difference. Before we move on, can you explain these two equations to yourself and tell yourself why do these two equations make sense, where do they come from, and how do they relate to wires and batteries? Okay. That is a little bit on the concept that we know as electric potential or electric potential difference. Oh, I almost forgot something. Wow, this was going to be very embarrassing. I almost forgot to talk about our units here. The units of electric potential difference are volts, capital V, which is why oftentimes electric potential difference is called voltage. But I will almost always call it electric potential difference because electric potential difference actually speaks to the reality, the physical reality of you have a difference in electric potential between two places, or sometimes I'll just call it potential difference. However, you'll also commonly hear this called voltage. And it does have units of volts. Okay, whew, now we're ready to talk about current. That was dangerous, guys. Did you see how that almost just happened? We almost just moved on without talking about units. Oh my gosh. Let's talk about a little bit about current. If you had to use one letter to represent current, you would, of course, choose the letter I. And we have a definition for current here. I say that current is the flow of charges from high potential to low potential per time. Current, I'll say it one more time so that you can get it written down. Current is the flow of charges from high potential to low potential per time. It's the flow of charges from high potential to low potential per time. When we talk about voltage, voltage is the difference in potential between one place and another place. It's that difference in elevation. Current is the actual movement of charges around that wire from the high potential place to the low potential place. Now, because current is a movement of charges per time, we have an equation for current that looks like this. We say that current is how much charge passes through a wire in a certain amount of time. If I had, I'm going to draw a little battery set up right here. Once again, not a Lego. If I had a battery set up right here, here's my high potential place. Here's my low potential terminal of the battery. This is positive over here. This is negative over here. If I wanted to find the current in this wire, what I would do is I would take a little look at this spot in the wire right, oh my, that was crazy times. Okay, I would take a look at this spot in the wire and I would count as I look at the wire and I'd count how much charge passes me by. And I'd say that's 1 coulomb, 2 coulomb, 3 coulomb, 4 coulomb, 5 coulomb, 6, 7, 8, 9, 10. That was 10 coulombs in 5 seconds worth of time, and that would give me my current. I would say my current in this case is 5 coulomb. Oh gosh, nope. Okay, I would say it's 10 coulombs in 5 seconds. And I would say it looks like I have a current of 2 coulombs per second. But all the good people of the world got very tired of saying coulombs per second, coulombs per second, coulombs per second, coulombs per second, and so we said we need a new system of units, and the new system of units that we used is amps, or amperes. The units of current are amperes, more commonly known as amps, and represented by the letter A. A lot of students like to use the abbreviation, where should I put it? Right here. CIA to remember all the things that they need to remember about current. They say current is represented by the letter I, and it has units of amps, or units of amperes. So that's a nice little tool that a lot of students use. Now, we have one equation for current, and that's that current is equal to charge per time, but you also remember that the total amount of charge that you would see flowing past you is equal to the number of electrons, the number of electrons times the charge on one electron, or Q total is equal to NE, like this. Well, we often like to plug that equation back into this thing over here, so we would say that the current that you experience is equal to the number of electrons that pass you by times the charge on one electron divided by a change in time. And both of these expressions are good ways of finding current, and both are good for your bag of tricks. The first expression, I equals delta Q over T, that helps you find the current in terms of how much charge passes you by. The second one, I equals NE over delta T, helps you to find the amount of current in terms of number of electrons. Now let's try a quick practice problem. Open up your textbooks to page 609, number 2. Here we go. Oh gosh, whoops. Page 609, number 2. Here's what it says. In a particular television tube, the beam current is 60.0 microamps. How long does it take for 3.75 times 10 to the 14th electrons to strike the screen? And then it gives you a hint to recall that an electron has a charge of negative 1.602 times 10 to the negative 19th coulombs. Okay, so here's what we have. We have a television tube that has a beam current. Here's how televisions work, by the way. The way that an old-timey television used to work is that you would have a screen here. Let me draw a little. Here's the screen. And do you remember when these televisions used to have like giant backs on them? Like they seriously used to be like this massive thing. Here's like the front of the TV, and here's the back. This is like a side view of your TV. Do you know what I'm talking about? It kind of had like vents on the side. Anyway, some of you are like, no, I've never seen a TV like that. I've only ever seen a flat screen TV, and the side of my TV looks like this, Miss Wilson. Okay, yes, but back in the day, it used to be like this, and the way that it would work is they would launch electrons this way. Whoops. They would launch electrons from the back of the TV towards the screen, and when the electron hit the front of the TV screen, it would light up that little pixel on the TV screen. And so that's how all little TVs worked, is that they just threw little electrons at the screen, and each little electron would hit a little pixel. When it hits a little pixel, then the pixel lights up. Now here's what this problem is saying. This problem is saying that those electrons that are moving through the TV, they have a current, a beam current, of 60.0 microamps. Remember that micro means times 10 to the negative 6th. And that's the beam current of the TV. What that means is that you get 60.0 microcoulombs of charge passing through that little beam per second. The question is, how long does it take? Sounds like a delta T to me. How long does it take for 3.75 times 10 to the 14th electrons to strike the screen? And then it says, remember that E, the charge on one electron, is equal to 1.602 times 10 to the negative 19th coulombs. Let's go ahead and try it. We'll start with an original equation. We know that I is equal to, I got two options here, delta Q over delta T or NE over delta T, and I'm going with the second one here because it looks more like what I have. So we know that I is equal to N the number of electrons times the charge on one electron divided by the amount of time that it takes for them to pass by. We rearrange and solve for what we're looking for, which in this case is time, and we get that the time is equal to the number of electrons times the charge on one electron divided by I. That then allows us to plug in numbers, and I think we're good to go here. I'm going to back it up though a little bit to give myself a little bit more space here to plug in numbers. My number of electrons is 3.75 times 10 to the 14th electrons times the charge on one, which is 1.602, times 10 to the negative 19th coulombs, divided by here my current, which is 60.0 times 10 to the negative 6th amps. And if I plug that all into my calculator, I will get a final answer here of 1 second. And that's it. That's a little bit on current. If you look at our goals, we have now discussed potential difference, electric potential difference, also known as voltage. We have now discussed current. Next, we are going to discuss resistance. Let's pull up a new page here. Resistance, let's change out our color. Resistance, and this is going to be a very terrible definition, and I do recognize that, and if you do hate me forever for this definition, totally and completely understand. Resistance is the resistance to the flow of charge. It's a resistance to current. It's the resistance that a conductor gives to the flow of charge. We represent resistance with the capital letter R. Don't ask me why we chose a variable that was so reasonable to represent resistance. And resistance in a wire depends on a few things. First, one thing that resistance depends on is what kind of material you have. If you have a material that lets its electrons flow very freely, then that thing will allow lots of current to pass through, because if it allows its electrons to flow very freely, then lots of charge can move per time. But if you have a material that you're using for your wire that is very stingy with its electrons and doesn't let many flow freely, then that material is not going to let electrons flow. So we say that resistance depends first on the resistivity of the wire. Resistivity is a constant. It's the letter rho, and it represents the exact resistivity for a given material. It differs for every material. So some materials have more resistivity and other materials have less resistivity. It really just depends on what type of material that you have. Then the next thing that it depends on is the length of the wire. You remember that we said back in the day, like a few minutes ago when we were talking about voltage, do you remember that we said that potential difference is equal to the electric field strength set up in the wire times the length of the wire here? Well, that means, if I rearrange a little bit, that the electric field that's set up in the wire is equal to the potential difference of the wire times the length, or divided by the length of the wire. That means that if I have, here's my battery once again, that has a certain potential difference, and then you have a wire connecting the high potential place to the low potential place. If my wire is very, very long, the electric field in the wire is a lot weaker. But if my wire is very, very short, like this, then my electric field is a lot stronger. Kind of like if I had a very long path between the soccer ball at the top and the soccer ball at the bottom. If I have a very long path versus a very short path like this, you know that you're going to be able to, that you're going to get a faster acceleration here than you will here. Ultimately, over time, it'll even out, and that's like a whole different thing. But here's the general concept: is if you have a shorter path, your electric field is greater. It'll pull harder on these things, and they'll run faster. If your path is nice and long, if you have a very long wire, then the electrons will travel a little bit slower around the wire. Oh no, I just remembered something that I needed to talk about with current that I totally forgot. Okay. I'll go back in and add it later. 1 second here. We'll talk about resistance first, and then we'll go back and talk about it. Okay. So, If you have electrons that are flowing in this wire here and you have a longer wire, that will create a less electric field, which means the electrons will flow slower. They're not going to get pushed as hard, and so you increase the resistance when you increase the length of the wire. The last thing that matters is the area of the wire. If you have a really, really skinny wire, and all the little electrons are all trying to march through the wire, all that little charge is trying to flow, but it's a very, very thin wire. Well, then it's going to be very, very hard for all the electrons to flow because they're all kind of bumping into each other as they kind of try to make their way through. But if you have a very wide wire is going to let a ton of current flow straight on through. All those little electrons will get to ride through. It's kind of like when you're on I-70 and you're coming home from skiing. And you know, when everybody narrows down to I-70, and you all have to narrow down into 2 lanes, and all of a sudden the traffic gets way worse because everybody's trying to flow through a very narrow section. Same thing happens in a wire. If you have a very narrow section of wire, all the little electrons get kind of cramped together and they can't flow as fast, versus if you have a wide open highway with tons of lanes and everybody can flow very quickly. So the resistivity of a wire depends on the resistance of a wire depends on the resistivity of a wire, it depends on the length of the wire, and finally it depends on the cross-sectional area of the wire. Before we go back and talk about current, can you please explain to yourself what are the 3 things that resistance depends on, and how does it depend on these things? Next, let's go back and talk really quickly about current because, oh gosh, I didn't even tell you this, and this is just embarrassing. There's this whole issue that we have with current. You remember that when I defined current for you, I said that current is the flow of charges from the high potential place to the low potential place. Well, here's the issue, is that current is the flow of charges from the high potential place to the low potential place. If a little positive charge was here, that little positive charge would love to run away from the high potential place to the low potential place. And in fact, the electric field that's set up in the wire pushes from high potential to low potential. So the electric field goes like this, and then like this, and then, oh gosh, and then like this through the wire, like so. The problem is we know that it's not actually positive charge that flows through the wire. The reality is that negative charge flows through the wire. Here's the problem. We discovered electricity before we discovered electrons. And so when we discovered electricity, oh gosh, why do we do this? Why do we do this? Please stop. Okay. Everybody settle down. Okay, sorry, now that we're all settled. We discovered electrons after we discovered electricity. So we said, oh yeah, we found this electricity stuff. And here's what happens is that you get charge that moves this way. And we're going to say that positive charge flows through the wire from here over to here. And then we discovered electrons and we found out that actually, in fact, that's not true. The reality is that negative charge flows from the low potential place to the high potential place. But at that point, we had already defined current as the flow of charge from the high potential place to the low potential place. So here is the difficulty, is that we say current is the flow of charge from high potential to low potential, and current goes this way around a circuit. But in reality, the electrons actually flow back the other direction. So current flows one way, but the electrons flow the other way. That is just the sad reality of where we are. I wish it could have been different. I wish we could have found electrons first. If I could go back and tell Benjamin Franklin about electrons, I totally would have. But here we are, and it's quite tragic as things are. This means that when we're talking about resistance to flow in the wire, we're talking about the resistance to the movement of electrons, or we can talk about it as the resistance to the flow of current. Both are really talking about the same thing, and you can use both ways of talking interchangeably. All that you have to know is that current is what we talk about flowing in a wire, but in reality, it's the electrons that are actually moving. So either way of talking is totally okay. And now, finally, to bring them all together, we shall talk about our last topic of the day. And our last topic of the day today is Ohm's Law. Ohm's Law brings together everything that we've been talking about so far. It brings together potential difference, it brings together current, and it brings together resistance into one beautiful and wonderful equation. Here's the idea. We say that how much current flows in a wire, how much those little electrons can flow, depends on 2 things. First, it depends on the potential difference. And second, It depends on the resistance. If you have a greater potential difference, that's like having a more positive place and a more negative place. It's like having a greater difference in elevation. Having a greater difference in elevation is going to cause the charge to flow faster. Delta Q over delta T is going to increase because you're going to get more delta Q per delta T. But if you have greater resistance in the wire, increasing the resistance in the wire is going to slow down the flow of charge. And so current decreases with an increase in resistance, and it increases with an increase in potential difference. And this equation right here is Ohm's law. Now, I always teach Ohm's law this way because it shows that current is the dependent variable on this side by itself, and current depends on voltage and it depends on resistance. But the more common form of Ohm's law looks something like this. It looks like delta V equals I times R. Same equation, just rearranged. The reason why I don't like this one as much is because the potential difference doesn't depend on the current and the resistance. How much current you get depends on your difference in potential and your resistance. So I don't like this one as much. But the nice thing about this equation is it is very reminiscent of your childhood. Do you remember this nursery rhyme, the one that's so familiar to you, the one that goes, twinkle, twinkle, little star, voltage equals I times R. Yes, and so you remember this one from your childhood, but this is the one that I like to use in class. Let's go ahead and try a practice problem. Go ahead and take a look at page 615 in your textbook, number 6. Here's what it looks like. Number 6 says the current in a certain resistor is 0.50 amps when connected to a potential difference of 110 volts. What is the current in the same resistor if the operating potential difference is 90 volts and then if the operating potential difference is 130 volts? Let's go ahead and try it. It says that the current is equal to 0.50 amps. I'm going to say that this is current 1. When the potential difference is equal to 110 volts. And it asks us to find what would the current be like if, actually I'm going to call this, because this is parts A and B, I'm going to call this current A. What would the current be like if the potential difference was equal to 90.0 volts? And what would current be like if the potential difference, what would current be like if the potential difference was 130 volts? Let's go ahead and try it. First, we're going to start here with Ohm's law, that I equals delta V over R. If I'm looking for current, then each time I have to plug in a delta V and an R. But what you'll notice here is that I wasn't given an R. Well, let's see if we can find it. We know that R, if we rearrange this equation, is equal to delta V over I. Now, I was given a delta V and an I. I know that R would equal delta V1 divided by I1. I could plug in numbers now to find this resistance, but then I'd be plugging in numbers before I do all my algebra. So here's what I'm going to do, is I'm going to say that IA is going to equal delta VA divided by R. And then I'm going to algebraically plug in R here. When I algebraically plug in R, I get delta VA divided by delta V1 times I1, or another way to write this is times I1 divided by delta V1. Now, I could plug in some numbers here. I have 90.0 volts for my delta VA. For my current initially, it's 0.50 amps. And for my initial voltage, it's 110 volts. Plug this into your calculator and you get something like, one second, let me double check. Something like 0.41 amps. Check and make sure that this makes sense to you. I just decreased my potential difference here. So if I decreased my potential difference, but I kept my resistance the same, then my current should go down, and you see that it does. It used to be 0.50 amps, now it's 0.41 amps. Could you do this problem and try part B by yourself? I hope so. Well, today we talked about quite a few things. We talked about voltage, then we talked about current, then we talked about resistance, and finally we ended today, I'll do a different color so that it all looks interesting. We ended today talking about Ohm's law. You learned that voltage or potential difference, electric potential difference, is the difference in potential between one place and another place. We related that back to gravity. Make sure that you really deep down understand what electric potential difference is. Then we talked about current, which is the direction of the flow of positive charge, even though we know that positive charge doesn't actually flow. It's actually negative charge that flows. And it's charge per time. We found two equations for that. Then we talked about resistance and how resistance depends on the resistivity of a wire, the length of the wire, and the area of a wire. And finally, we related that all to Ohm's law, where Ohm's law says that current is equal to the voltage divided by R. And that is all for today, folks. I hope you have a wonderful, wonderful rest of your day, and I'll see you all next time. Bye, good people.